All right, today we're going to take a look at section 2.3, which is set operations and Cartesian products. Cartesian products actually is a set operation. The section title differentiates them, so I did as well, but it's actually one of the set operations that we're going to be describing. All right, the first one that I'm going to talk about is intersection of sets. An intersection of sets is the set of elements common to two or more. It could be more sets. So the key idea here is this word common. So you've used the word intersection before. You've used it in a lot of ways. Intersection you've used in a math class in algebra where two lines cross each other, right, where they intersect. You've also used it in a very contextual sense when you talk about the intersection of two streets. So right outside the building here, we have Kickapoo and MacArthur, and they cross. And when we talk about their intersection, we're talking about the physical place that is on both streets, okay? And that's exactly what we're talking about in this section as well when we talk about intersection. We're talking about what they have in common, where they meet, where they cross. So we've got an example up here, and you'll notice some notation. The notation for intersection, if we have two sets A and B, an intersection symbol is an upside down U, or a horseshoe shape. Okay, so when you see that notation, that means intersection. Again, that's the math lingo, right? The texting kind of language for what we're doing. Okay, so we have a universal set U. It has items from A to G in it. We have a set X, which is A, C, E, G, a set Y, which is A, B, C, and a set Z, which is B, C, D, E, and F. And the question asks us to find Y intersect Z. Now, the first thing we're going to do is to recognize that this is a set, so it's going to be in curly braces. Okay? I'm going to close the curly brace when I'm done. And I want to list the elements that are in both Y and Z. What do I get? B and C. And then I close the curly braces. All right, so this is a set that has two elements, and it's the set that's common to both Y and Z. All right, the next set operation is the union of sets. So this is a set of elements that's in either or both / all sets. Either set or both. The notation for this one is a U, which is really nice for union. Okay, so I want you to picture or imagine a wedding ceremony, okay? So one of the phrases that the preacher will say is something like this: the two became one, right? It's a union. And what that means is that your house is now my house, and your kids are now my kids, if there are kids already involved, right? And your debt is now my debt. We get it all. Everything that's yours is mine, for good or bad, right? That's what's going on with a union. Everything that's yours, everything that's mine, we join it all together and we create something new. Okay? So a union does the same thing in this sense here. We're taking a look at the exact same sets as before, Y and Z. All this is the same. And this is union, which means I need to list everything that's in Y, that's in Z, or that's in both of them. That gets included too. So again, it's a set, starts with a curly brace. What's in Y or Z, or both? So we have A through F. A, B, and C, which were all in Y. B and C were also in Z. And then we've got D, E, and F because they were present inside of Z. Almost the whole set in this case, right? Almost the whole universal set U. Not quite, but almost. Okay, there's one more that I want to show you the math for until I I have a concrete sort of a visual example of this. The next one is called difference of sets. What does that word difference mean? You hear the word difference, what do you think? Subtraction. And the notation for this does in fact look like it is subtraction. We're not going to think of subtraction in exactly the same way here because as you see there are no numbers, right? I mean, like I could count how many things there are, but that's not what we're talking about either. We're talking about removing something because that's another idea or a concept related to subtraction, right, is the removal of something. So I want you to think about this difference or this subtraction as a removal. So the difference of sets is the set of elements that are in the first set and are not in the second set. So everything that was in the second set gets removed out. So what you do is you take a look at the one below, and we start with the first set, which is X, right? X is listed first. So we're going to look at set X over here. We have 4 items inside of X. And this difference means I need to remove the items that are in Y. So we start with A. A is in set X. Is it in set Y? Yes. And because it is, it gets removed. Look at the second one, C. C is in X. Is C in Y? Yes. And since it's in Y, it gets removed. Look at the third one, E. Is E in Y? No. So that's the very first one that I get to list as being inside of this difference. G? It's not either, so we get to list it as well. Now, that's it. Notice we do not include the C from down here. I'm not taking like the pieces that are sort of on one side or the other and then just writing them all down. I take everything from this set and I'm only removing items. I'm not including any extras. Yes, Leah?
Isn't B in the set?
Yeah, it is. That's what I just said when you were raising your hand. Okay, that was what I was just addressing, is that this is not going to introduce extra elements that were over here. Go back to the description. This says this is a set of elements belonging to the initial set. It has to be inside of X. And then taking it out, removing it if it's also in Y. Yes?
Well, B doesn't belong in X. Is that correct?
That is correct. That's why it doesn't get listed down here.
Oh.
These are only the items that are in X, and we
Right.
remove the items that are in
The
Y.
secondary set.
That's a really common mistake, actually. Okay, so probably 3 or 4 of you, when it comes to the test, are going to do this for me. You're going to include extra things that aren't supposed to be there. Remember, all this is removing things from the first set. It's just a removal. It's not actually making the set any larger than set X was to begin with. No new additional items. All right, I want to give an example before we go to Cartesian products of, hang on just a sec. Okay, I want to give an example of how this can verbally be played out, okay? So I have a brother-in-law, his name's Adam. He's my husband's brother, Adam. And Adam was married a long time ago at one point, and he had a daughter named Madison. And he's not married to that first person any longer, and he has since remarried. It's been quite a while. His wife now, her name is Jody. Okay, so he has Madison from his first marriage, and then he and his wife now, Jody, have 2 children. They have Adam and Jocelyn. So we have little Adam and we have Jocelyn, and she's expecting as well, but let's just talk about Adam and Jocelyn. All right, so we could actually talk about the intersection, the union, and the difference in these sets. So we're going to talk about the sets being this collection of children. Okay, we've got Adam's kids. Adam's kids include Madison, oldest kid, she's probably this tall. Madison, we've got little Adam, and we've got Jocelyn. Those are all of Adam's kids. Jody's kids, biological. Okay, so I'm not trying to step on any toes here, but I just need to talk about biological to make this work. Okay, Jody's biological kids only include Adam and Jocelyn. Madison's not hers biologically. Okay, so we could talk about the intersection of Adam's kids and Jody's kids, and what is the intersection of their kids? The ones that are biological of both of them, right? So it's the two little ones, Adam and Jocelyn here, the little ones, okay? We could talk about the union of their children, and that would include all three of them, right? We've got Madison, Adam, and Jocelyn. All three of them would be the union. We could also talk about the difference of sets. That is, we could talk about Adam's kids minus Jody's kids. So if we took Adam's kids, which is all three, and we subtract out the ones that Jody has, we're left with Madison, okay? So this is an idea of sort of just talking about yours, mine, and ours, all right? All right, there's one more operation we're going to talk about today, and this is Cartesian product. All right, so Cartesian product has to do with ordered pairs. You've seen ordered pairs before. Where? Where? Graphs. You've done it with graphing, right? You've seen points X and Y, and you've plotted them. X is the horizontal and Y is the vertical and all of this. This has the same feel to it, okay? These are ordered pairs A and B. A is an element of the first set A, and B is an element of the second set B. The little a is called the first component. The lowercase b is called the second component. And in general, this point AB is not the same as the point BA. And if you think about that from a graphing perspective, you remember that that's true, right? Sometimes it could work, right, if you had the point 3,3. Obviously, it doesn't matter. But if you have the point 3,2 and the point 2,3, it's not the same location in space. Okay, so our Cartesian product then is the set of all items AB, where A is in capital set A and B is in capital set B. And it has a notation. So on this page, before we flip to the next one, the Cartesian product is an X. Hence product like multiplication, right? All right. So when you see A cross B, it actually means I'm going to have ordered pairs. So I'm not really multiplying anything, okay? I'm going to have a list of ordered pairs. And we're going to do an example so you can see how this is going to work. Okay, so we should be getting familiar with this list of U, X, Y, and Z because we've used it several times now, right? All right, so the way that this works is I need to take every element of the first set X, so over here, and write it as an ordered pair. So the first item in set X is what? A. And let me join it with the first item in set Y, which is also A.
Do I have to use the curly braces?
We have to use parentheses right now. We'll bring curly braces back here in a minute, but right now these are ordered pairs, and ordered pairs are in parentheses. Now I'm going to list the first item in set X with the second item in set Y, which is B. Then I'm going to list, finally, the first item in set X with the third item in set Y, which is C. That is all the ways I can list the first item in set X with everything else in set Y. But that's not all. What do I have to do next? The second item in set X, which is a C, with the first item in set Y, which is an A. Okay, so we're doing this in an organized way so we don't lose track of somebody and forget to include something. I mean, that's why we're doing it, right? So then I'm going to do C and B, and then C and C. Does everybody see where all those came from? Am I done? No. I need to list the third item in set X, which is E. E what? EA, and then EB, and then EC. Almost done. Last item in set X is G. So I've got ordered pairs G A, and then G B, and then G C. Right. All right. So, but coming back to Leah's question about curly braces, these are the items in my set, but this is still a set. It's just a set of ordered pairs, which means I do need curly braces, but the curly braces go around all of the ordered pairs like this. Okay? So we don't list the ordered pairs in curly braces because they aren't sets. we list the items inside as ordered pairs in parentheses. And this is a collection of ordered pairs, so it is a set itself. You've got to have that notation correct or I will count off, okay? Parentheses inside, curly braces around all of the ordered pairs in parentheses. Okay, now just for a moment, I want you to tell me how many items are there that you just listed here? There are 12 ordered pairs. Now we talked about notation last class, in fact maybe the last two classes, for cardinality. It's the in front and then you put the set inside. Well, this set has notation x cross y. And you just found out that the set that you created has 12 items in it, right? There's 12 ordered pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 ordered pairs. Now, if you were wanting to, if you were told to create the set, you'd have to do this anyway, and you could count the ordered pairs, and that's great. But what if you were only told to find the number of items? Well, if you were told to find the number of items, it would be helpful if there was a way to do that without writing all the items out, right? Yeah. So taking a look at this idea, if n of A is the number of items in set A, all right, so n of A is the number of items in set A and n of B is the number of items in set B. Then if you're only wanting to find the number of items in their Cartesian product, you can actually take the number of items in A and multiply that by the number of items in B. That doesn't find you the set, right? It just finds you how many items would be in the set if you were to find it. So if you had some sets that were rather large, like what happened if you were wanting to find U cross Z? Do you really want to list all of these guys out with all of these guys out one by one? Not if that's all you were asked to do was to find out how many items were in the set, right? It'd be great to have this shorthand way of doing it. So let's take a look. This is the same problem we just did on the previous slide, but we're going to do it with this shorthand notation to find the number of items. So this formula says I should be able to take the number of items in X and multiply that by the number of items in Y. How many items are in X? 4. How many items are in Y? 3. And 4 times 3 is 12. The same 12 that I got on the previous slide, right? But done in a very different way. Let me say it one more time, though. Problem number 4 didn't ask me to find the number of items. That's not what this said right here, was it? So if you were encountering this problem number 4 and you told me how many items, you wouldn't be giving me what I asked you for. Problem number 4 asked you to find the ordered pairs. I just continued to the question below it and wanted you to identify how many ordered pairs there were. Does everybody see the difference in those questions? Because those are not the same question. Okay. All right, so we talked in the minute ago saying that we were going to do a whole bunch of set operations. We saw one of these set operations last class period. This is the first one. And what I want us to do here in this set of slides, and it's a box at the bottom of your page if you're taking the notes from online. So there's a box that has you fill in all these set operations. And what we're going to do is we're going to fill in the set notation for these. So the first set operation we actually encountered was the complement. So does anybody remember what that notation looked like? Right. It looked like an A with a slash, right? A prime, or a complement. And we're going to define what that looks like in terms of sets. So set notation always starts out with a curly brace. The set has items that are X. We did this the very first day of class, right? You guys loved it, I remember. And then we do the bar that means such that. And then after this, we're going to describe what in the world X is. So what is X? Well, when we encountered this last time, the first thing we said is X is in the universal set. What else did we say, though? What does it take to be in the complement? It's not in A. And we had notation for that last time as well, didn't we? It was that element symbol with a slash through it. And we drew a picture, and I want to draw it again here as well. We're going to draw a few pictures on these slides because they'll help us in a minute. We had this sort of an idea. Where this is set A, and this is set U. And if I were shading it in, which is what I'm going to do, A complement is the outside part of the circle. It's outside of the circle, but inside the rectangle still. So this piece right here is A complement. Inside of the rectangle U, outside of the circle A. Okay, intersection though we did today. All right, so the intersection symbol was which one? What goes between A and B? The upside down U. That's intersection. Some people think it looks a little bit like an N, like a lowercase n for intersection. So you can think of it that way too if it's helpful. And this is a set. So it's the curly brace, the X, and the bar. Okay, all that's the same. What does it take to be in the intersection?
They have to have both the same elements.
The element has to be in both sets, I think is what you mean, right? So how could I write that in lingo, math lingo? I'll start you off. That will make sure it's in one of the sets. What do I need to do next? Yes. Something needs to go between them. What do you think should go between them? Well, it will already be in the universal set if it's in A and B, because A and B are in the universal set. So we don't have to worry about the universal set on this one. What should go between X's in A and X's in B? I need a word. No? Close, not a plus. No? Oh, somebody said and. Who said and? That's right. That's what we want. And. Right? It has to be in the first set and in the second one. Both of them at the same time. The word's and. And that's actually a really important word, which is why I wanted you guys to think through it, because we're going to encounter one more definition here, and you're going to see why. Oh, let me draw a picture. All right, so we have our rectangle. We have two circles. Right? We talked about Venn diagrams a little bit last time. Here is set U. Here is set A, and here is set B. Which part of this picture represents the intersection?
The inside of the two circles of A and B.
Right, where they overlap, right? Just like the overlapping streets outside. It's this sort of football shape inside here. This piece right here is the piece we're talking about. That's the intersection. Okay, the next one we did was union. So the union symbol was what? It was a U, yeah. And we had X such that. So what did it take to be in the union? What was it?
Said a civil war.
A civil war. Thank you, that was awesome. Okay, what did it take to be in the union of this union? A wedding ceremony, right? Isn't that what I said? Well, yeah, sort of. So what does it take for those children to be Adams and or Adams and or Jody's kids? What did it take?
They had to get married.
They had to get married, okay. They had to join, and they had to be one or the other's kids, right? I mean, like, my kid doesn't get to be counted in that mix because they're not their kid. So we get one of them, X is in A. The other one, X is in B. What goes between them here? Or. The word or goes between them, which is different. That's the only difference, right? Between this description and the last one is that word. I want you to be really careful because the word or here can be understood in English two different ways. In English, we use the word or to mean the exclusive or and to mean the inclusive or. This is one of those wonderful English things. This is why I don't teach English. We can say or, meaning it's yours or it's mine, right? We can also say or can mean it's yours or it's mine or it's both of ours. That's an inclusive or, and that's the one we're using here. Yours, mine, or both, okay? So you've seen the movie Yours, Mine, and Ours, maybe. Okay, this is a movie where two families get married, okay? And they both have kids from before and whatnot. There's your kids, there's mine kids, and if we had kids together, they'd be our kids. So all three of those descriptions would be described here. Yours, mine, and ours, all of it, either or both, okay? Now, pictures. We've got that same set of overlapping circles that we had a minute ago. This is set A, this is set B, and it's inside of rectangle U. What part of this picture is represented by the union? Everything inside both circles, right? Including that overlap in the middle. Yeah? Yeah. So we get all of circle A, we get all of circle B, and we get the part that they have in common. That's the ours in the yours, mine, ours description, right? So we get everything inside the circles. That is the union. Okay, what did difference look like? What went between A and B when we did difference? A minus sign, a subtraction sign. All right, so the set starts out same way. It's all x such that what? What does it take to be in the difference? Has to be an A. Good, that's where we'll start. X is an element of A. What else? And it has to be not in B, exactly. And we would put the word and between them. X is not in B. Right, we remove everything from X that was in set B. I'm sorry, remove everything from set A that was in set B. All right, so picture form. What part of this picture represents A minus B?
A without the overlapping area.
That's exactly right. So it's sort of this outside part of A. Right? It's all of circle A and remove the part that crosses over into B. We don't add anything extra from circle B, do we? Just removed a piece of part of it that sort of overlapped with B. All right, Cartesian product. That was the one that looked like a multiplication symbol. Whoops. This one's a little bit different. So pause with me. Don't write x bar. It's not going to be x bar. The Cartesian product included elements that looked like what? Ordered pairs. So this is going to be ordered pairs, and I'm going to use, just for the sake of being clear, 2 letters. Okay? First letter X, second letter Y, and we're going to have a bar. What has to be true about this little letter X? Where did it come from? What's that? It is in the universe, more specifically. It has to be in set A. So the first coordinate has to be in the first set. So that first coordinate X has to be in the first set A. What about the second one? And Y has to be in B. I mean, that's how we made those ordered pairs. Remember that? We paired up everything in the first set with everything in the second set. And there isn't a picture form for this because I'm actually creating a different kind of set. It's not a set from the original elements. It's a set of ordered pairs. All right, so here's why we actually worked a little bit with those picture forms. The other thing you're going to be doing in this section, besides looking at lists and identifying which piece is in what list, is you're going to be looking at a diagram of them. All right, so this is Venn diagrams, and we're going to draw a rectangle. And I'm about to show you how I expect to see your stuff done, although I'm perfectly aware that there are other ways of doing this. This one lends itself really well to what happens on your next problem. Okay? So we've got set A, we've got set B. And what I want you to do is this. I want you to number the different sort of regions of this diagram. So this is one region, this is a second region, this is a third, and this is a fourth. And you wouldn't have to use numbers. Lowercase letters would work or whatever. Numbers is kind of what I tend to gravitate towards in this, just because I don't want it to get confused with these letters that are already here. They don't have to be in this order. I mean, if you wanted to put the 1 over here, 2, 3, and 4 here, that would be okay. Your picture when you get done is going to look the same. So here's what you're going to do. On the side, I expect you to write down the first set is A prime, because that's what it says at the beginning, A prime. And what numbers are inside of what would be considered A prime? 1 and 2?
3 and 4.
3 and 4. A is set 1 and 2. A complement means outside of set A, right? Not in A. And the items that are not in A are 3 and 4. So we list 3 and 4. And the other set that we're supposed to be working with over here in this original description was set B. So what numbers are represented by, or what regions are represented by numbers in set B? 2 and 3. And then we're going to do something you did basically back in elementary school. We're going to draw kind of a line underneath it, right? Kind of like when you did addition or subtraction. You said this minus this, and you put a line, and you said, after this, I'm going to do something else. And you're going to look at these two items with whatever operation you were told. This particular one you were told to use was, what symbol is this? Union. What does union mean? Say louder.
What do they have together?
Together meaning what?
Like what's in each of them?
Each of them meaning both? Combine? Okay. So we want to make it or, right? One or the other or both. So we include everything when we do a union. All right. So what numbers are included in everything here?
1, 2, 3, 4.
2, 3, and 4, not 1. Why not 1 actually? 1 wasn't listed in A prime and it wasn't listed in B. So we're only going to include the items that were listed sort of above my line. Okay? Now, I expect to see this bit of work. If I don't see this, you're going to lose big points, because then I have to worry about whether or not you guessed or you looked at somebody else's paper or how in the world you figured it out. I understand on this problem, some of you can reason this out without any numbers. But that becomes increasingly more difficult with the next problem. So that's why I'm establishing this pattern right now, okay? But we're not done. What are the directions tell us to do? Shade. So we need to do that. We need to shade the regions that I just wrote the numbers down for. So we'll shade number 2, we'll shade region number 3, and we will shade region 4. So the only thing that does not get shaded is the outside area of section A. Does this make sense? Okay. Now, I forgot to look at this last time, and I was told that this picture did not match my numbers on your paper, so let me fix it. Does this say what yours, oh, this should say number 7, but does this say what yours says? Yes? It matches? Okay, good. I know what was wrong with that last time. Okay, what's different about this problem from the last one? There's a C. That's the big difference, right? There are 3 sets here. So I need to draw a picture that has 3, what? Circles. Whoops, that wasn't a circle. That one more or less looks circular. So we have 3 circles, they overlap. We start to look like it would be like the Olympic rings, right? If you want to follow the way I set mine up, I do A at the top, B, and then C at the bottom. So without telling me exactly where we're going to put them, what are we going to about put in here next?
Numbers.
Some numbers. We need some numbers to represent these different regions of my graph. And I'm going to start over here with circle A and put a 1. I'm going to put B in the overlap on top. I'm sorry, 2 in the overlap on top with A and B. 3 over on side B. We're going to put 4 in this overlap. 5 in the dead center, 6 down here on the bottom corner, 7 in C, and then 8 out here with U. You do not have to put those in those places. Your picture will still be the same in the end. Your numbers will just be different in the middle if you choose to do them differently. All right, we are going to do A first. Okay, just like when you were doing an algebra, order of operations says you do things inside of parentheses first, right? This is yes. Yes. So inside the parentheses, we have A and we have a B, and we're supposed to do their intersection. So I'm going to list set A first. So what numbers are in set A? 1, 2, 4, 5. What numbers are in set B? Because that's the other thing in parentheses. 2, 3, 5, and 6. And I'm going to do a line because I need to join sets A and B with what operation? It's not addition. It's no, it's not subtraction. Intersection. The symbol is actually an intersection. What does intersection mean? What they have in common, exactly. And what do these have in common? 2 and 5. So I've got 2 and 5 listed here. So I have just found everything that's inside this set of parentheses, right? And I want to join that with set C, so I need to list what set C has. So what items are in set C? 4, 5, 6, 7. Exactly. And then I'm going to join these together again in the way that it described above, which is with what operation? Union this time, right here. What does union mean? Intersection is what they have in common. Union is combining it all together, right? Is a combination kind of an idea. So I list everything. So what will I list here? 2, 4, 5, 6, and 7. And then if I come to my picture, what am I going to do? Shade those values. 2, 4, 5, 6, and 7. Make sense? Okay, got one more. I guess I just didn't change my numbers when I made these slides. This was problem number 8, isn't it? Okay. That looks like yours though, right? Okay, so I draw my rectangle and I draw my 3 circles, right? Okay, that was not a good C. And then what am I going to put in those areas? Numbers. I always do mine the same way, so pick a way that you like so that you won't get mixed up when you're looking at them. I'm going to go with this. Looking at this statement right here, what am I going to list first? A, the items in set A. What items are in set A? What numbers? 1, 2, 4, 5. Now what am I going to do? B complement. B complement means what? Things that are not in B. So what numbers are not in B?
1, 4, 7.
Awesome. 1, 4, 7, and 8, right? Looks good. Now what am I going to do with these 2 sets? Combine them with what operation? Intersection. What does intersection mean? It means what? What they have in common. What do these have in common? 1 and 4. Okay, great. Now what? Now we find C complement, right? So what items are in C complement? I think you guys are getting the hang of this. 1, 2, 3, and 8. Right? Everything not in C. How am I going to join these 2 sets? I'm intersecting this time, right? What does intersection mean? What they have in common. And what do these have in common? 1. So when I come over and I shade, the only region I will shade is region number 1. Please understand, if you do not show me this work, you don't really get any credit on these problems. You have to show these number sets out. Yes?
Do you want the circles on the corner visual work?
No, I don't care. No, that was just a visual for me. Yep. Any questions? All right.